So let's discuss kind of our main topic today. Main topic is obviously parallel lines and the angles that are involved in them. So yesterday we started two properties. So I want to discuss those properties right now in case you were gone or in case you just tend to forget kind of what we were talking about. So here's my parallel line. So let's start with a quick review. So I don't care how the parallel lines are drawn. Remember, the little arrows that your book will provide you will kind of give you a little hint that, you know, the lines are going the same direction. So those two lines are parallel. We have a transversal running through them and all that. So I don't know if you online can see that. Let me drag this out here. Put that camera more to the center. This will look weird, probably giving me motion sickness. Yeah, it looks okay. All right. So anyway, so we have our parallel lines, we have the transversal cutting through it, and what we discussed yesterday was that first postulate, postulate number 3.1. Okay, postulates 3.1. Now again, let's talk about the definition of the postulate. Postulate, it's a mathematical statement, a property in geometry and mathematics. We accept it as truth without the need to prove it, without proof, right? The reason being is that we have to start somewhere. It's a fundamental in math, right? It's the same concept of like 1 plus 1. That arithmetic, you know, is so basic in nature that you can't prove it unless you just know definitions, right? You can't prove that 1 plus 1 is 2 unless you know the definition of just what number 2 means. It won't make any sense to you. All right, it's kind of like learning a new language. You don't know what the words mean until you know the definition of them. Then you can use them in a sentence. Well, the idea with 3.1, it was based on corresponding angles. Corresponding angles. So they call it, in other textbooks, they call it the corresponding angle postulate. They actually just give it that name. Corresponding angles. Let's talk about the three rules. What are the rules for corresponding angles? Like, how do I know if it's a corresponding angle or not? What are the three stipulations? Give me one of them if you know it.
They have to be on the same side of the transversal.
Good. So this is the transversal, right? This is my transversal T. I have to be on either the right side or the left side on this particular diagram. On the next pictures I'll draw it differently, okay? So they have to be on one side. Good. Somebody else.
One has to be on the top side of it, and on the exterior, one has to be on the interior.
Yeah, good. One has to be inside the two parallel lines. So think of it like a sandwich inside. So one of the angles has to be in here, and the other has to be on the outside. But they, again, just like we said before, one inside, one outside, but on one side of the transversal. Okay? Thank you for those. Somebody else now, what is the last stipulation?
They can't touch.
They cannot physically be touching. That's called adjacent, right? They're physically next to each other. So one's inside, one's outside, and they're not physically touching, and they're on one side of the transversal. Those are corresponding. Does that make sense? Now, I could put them anywhere. There's a lot of pairs of corresponding angles up there. I just picked that one specifically. Now, what this postulate said, those are equal. Whatever the number is. I'll let you guys pick a number here in a second. So just think of a digit. I don't care what it is. So they are equal in terms of number. Okay? That's what this postulate says. If the lines are parallel. It was a conditional statement. If the lines are parallel, then these angles have the same measure. They're the same digit. So somebody throw out a random number.
5.
5. Boom. We'll go 5. Let's say this is 5 degrees. This one is also 5 degrees. Automatically. You can transfer that down. Now, again, why? Well, we don't prove this, right? We don't prove it. There's no evidence to be shown. The only thing I can do to show it is to put a protractor down, you know, that mathematical protractor where you measure angles, and see that it works. That's the only thing I can do. There's no other trail I can go down to show why it would work out to be the same number every single time. That's why it's a postulate. There's nothing to fall back on. It's a fundamental, right? If you don't know how to read a protractor, there's nothing else we can do for you, right? So in fact, I'm gonna pull out a protractor just so you can see this. Now it's not gonna be 5 degrees, obviously, but I'm just gonna bring out one of my protractors here. Let's see. Protractor. I'm gonna add it somewhere. Okay, protractors go from 0 to 180. There's always two sets of numbers, right? Depending on how your angle's drawn. I always try to line up on mine. I have to line up this little arrow with my vertex, and then you just kind of turn it so you line up one of the walls with 0. So I'll do it like this. So line up my vertex with that little arrow, line it so 0 degrees, and now I'm going to count out 10, 20, 30, 40, 50, 60, 70, it looks like about 72, right? And then if this line is truly parallel, kind of looks close, it's not the greatest, I freehand drew it, so it looks okay. This should be around 72, right? Well, if they were perfectly parallel, it would be exactly 72. So I line up 0, 10, 20, 30, 40, 50, 60, 70, it's a little bit over, but you get the idea, right? They're supposed to be the same digit. So that's the idea. Questions on the postulate from yesterday? Okay, now you're thinking, okay, what are we going to do with that? This is what we're doing with it, right there. We're going to be transferring numbers on a picture. So if I give you a picture with digits, we're going to transfer those numbers around the picture so you can easily go, okay, this number is this number is this, and it bounces around. Questions? Okay, now let's get to the second property we talked about yesterday. So the second property was a theorem, right? That was Theorem 3.1. And again, how they number these, because I know it seems kind of weird, like why do they come up with these weird digits? It's whatever unit, whatever chapter you're in. So your chapter in your textbook is chapter 3, so they always start with the number 3. And then the number that comes after it is what postulate or theorem you're learning. So this is the first postulate, the first theorem that we're learning in chapter 3. Okay? Postulates, I think there's 14 or 15 postulates total in the book. We don't see them all. We'll just see a select few this year. And then theorem, there's a lot of theorems. Okay, a lot. In fact, I've skipped some because we're going to eventually come back to them. I kind of backfill. You will not see them all. Sorry, if you really want to see them all, they have them printed in the back of your textbook. You really want to go through every single unit and every single theorem. I only cover the main ones we need. So, but Theorem 3.1, it talks about alternate interior. Talks about alternate interior angles. So again, in other textbooks, they call this the alternate interior angle theorem. That's what they call it. They have a name for it. So let's talk about the definition of alternate interiors. Let's talk about that. What are the stipulations for alternate interior? There's a couple different rules. Give me just one.
Opposite sides of the transversal.
Opposite sides of the transversal. That's what it literally means to be alternating. So one's on the left side of the transversal, one's on the right, since my transversals go up and down. Next.
Inside.
Inside, good, because it's interior, good, obvious, good. One more stipulation.
They can't be touching.
They cannot be touching. They can't be physically side by side, so non-adjacent, right? So let's come up with our same little markers here. So again, they're both inside. One's on one side of the transversal, one's on the other, and they cannot be physically touching. So something like this, right? So whatever those numbers are, those are alternate interior. What this theorem says, they're equal in terms of measure. So give me any number. I know you guys made up 5 earlier. Make up any other number you want.
52.
52, okay? If this is 52, what this theorem says is that the other alternate interior, this one, is also the same number. That's what it says. Now, what we talked about yesterday is this is a theorem, right? Theorems it's a mathematical statement, but we have to prove it, right? We don't accept it unless I show you evidence of why it works, right? Because there is an actual evidence trail I can follow that will show why those have to be both 52. There is something I can actually show you that it will work, other than just putting my protractor up on the board. Now, the vocab word I talked about yesterday, it was called a vertical angle. And that's something I want you guys to see today, that it actually works. That's something we're going to look at over here today. So vertical angles. Vertical angles are where you draw straight lines that cross. So if you use a straight edge and you draw them, the angles that are funneled together, like this angle right here and this angle over here that are funneled together through like a little funnel system, they're always equal, no matter what. Now, here's the reason why, and I want you to see this today, why these would actually work. Okay, so let me move this desk in here just a little bit. Hopefully they can see that at home. All right, here's the reason why vertical angles always match. Why those two angles are always the same when they go through that little funnel system. Question?
Would the other side of the funnel on the 52, would that also be 52 then?
Yes, that's what we're going to talk about. That's exactly why this works. So you're going to see that. Yes. So hold on to that. I'm going to come back to that here in a second. So yeah. So vertical angles, they're the ones straight across, right? The little funnel. Okay. And we're going to use that here, just like mine was saying. So here's why. Okay. When you talk about straight lines, right? Just in general, just I drew the straight line. This line right here is supposed to represent that line right there. Sorry, it's not tilted the same way. What is the angle for a straight line? 180. Every single time, right? It's a full protractor. You can see it. If I put my protractor up here, it's going from 0 all the way to 180. Well, that's the same idea here. The full angle is 180, right? That full angle is 180. Whatever these two angles are, they add to be 180. They're called a linear pair. It's called supplementary. We have a lot of words, right? They're called a linear pair, okay? Well, here's the thing. I know these add up to be 180 because of the straight line. Okay, over here, same exact idea. This was a straight line going this way. So again, these have to add up to be 180. It's a full protractor. Well, here's the thing I want you to think about. In both cases, right, the one going this way and the one going this way, do you agree that this angle never changed? It was the same angle in both pictures, right? It never even changed. Whatever this number is, let's say this was at 80 degrees, right? So if this was going this way, right? This, these two angles here, this has to be 180, so this would have to be 100, because that's 80, and this would have to be 100 to add up to be 180. Same thing over here. That angle didn't change. That's still 80. And so over here, this one also has to be 100, because it has to add up to be 180. It's forcing the two that are funneled together to be the same because they're not changing, right? This wedge piece never changed. So it's forcing these two to be the same number each and every single time you see it. That's what's actually happening here. You have a bunch of straight lines. So just like what Maya was saying, the little funnel system across from 52, right? This can funnel over to here, and this would also be 52. Right? And same up here, it would funnel up, right? This would funnel over to here, and this would also be 52. Well, the reason why this theorem works...
I couldn't hear what
Shut up, Siri. All right. The reason why this works, right, is because of that postulate we just talked about, Postulate 3.1, all the corresponding angles. Well, when I did my little funnel system, right, I took my 52, funneled it down. I'm going to get rid of this one just right now. Right? And I funneled this straight down to here. This made corresponding angles. And so the corresponding angle here would be 52 because corresponding have to be equal. And then when you funnel it, it forces the alternate interiors to be the same. So no matter how you look at it, it's forcing the angles to be all matching. And then same, if I drew that angle up here, this would also be 52 because again, corresponding or alternate interior, however you want to see it. Questions? Okay, so when I look at a picture like this, when I know that lines are parallel, there's a lot of angles that are automatically the same digit. Like automatically, I can start bouncing numbers around the picture really, really fast. Alternate interiors, funneling to the other spots, and I can start transferring numbers all around the picture, and I can start hopscotching everywhere, and I can fill in a ton of numbers. So that's what I want you to get that sense of. How do I transfer numbers? So, but again, it's really relying on this concept of that straight lines add up to be 180. And so you can see that concept of why that works, why the funnel system works. Okay, again, it's called supplementary, linear pair, you name it. Okay, questions with the stuff from yesterday? Okay, we have two new properties today, two. I don't want to talk about them today. They're actual theorems, so we will have to show why they work. So we're going to go through them here in a second. But I think it's important that we get to review stuff. Number one, you tend to forget stuff, but also some people, just need to see that one more time to see maybe it makes more sense the second day seeing it. So, new theorems here. I'm going to probably try to use the same picture. So I'm going to get rid of some of my markers here, but I'll keep using the same drawing over and over and over, so hopefully that makes sense to you. So, all right. Let's get rid of all these markers. Okay, so new theorems here. So new theorems. So now we're on the second theorem now. So this is Theorem 3.2. So it's chapter 3, the second theorem we're going to learn. if two parallel lines are cut by a transversal, then they're, now I'm gonna put what the book has, and then I'm gonna reword something here, so you're gonna need to leave a little bit of a blank here. They're consecutive interior angles are supplementary. Okay, I'm going to have you write that down. Now, the word that I want you to leave a little blank next to is this consecutive interior. Maybe you want to leave like a little blank right next to that or below it. I'm going to fill that in with a better word because we haven't seen this word before. So this idea of consecutive. Maybe in Algebra 1 you've seen it, but I don't like the way the book used that. Okay, two parallel lines cut with a transversal. If you haven't noticed, all the theorems we've done up to this point have the same wording for these. Parallel lines cut with a transversal, consecutive now, consecutive interior angles are now, and I'm going to underline this, they are supplementary. Notice it didn't say that they're equal, not congruent. They're supplementary. That was a word I just used a little bit ago. All right. Now, the word I had you underlined, I told you I wanted you to leave a little blank next to where it said consecutive interior. That's what your textbook says. Other textbooks use a better word. In fact, it's a word you've seen before. Instead of consecutive interior, same side interior is a better word. That word is the word I'd like you to put next to this. For some reason, your book likes to use consecutive interior. And all my other geometry books, I have 5 books I've taught out of over the last 15 years. They always use same side interior, except for this new book. It's a new print. It's almost brand new, right? It's 2 years old. So I don't know why they're moving away from same side interior. They're calling them consecutive interior. It's the same thing. Consecutive in algebra means one after another. They're like side by side, basically. Okay, so same side interior. So we have to pick interior, so duh. But same side, they're on the same side of the transversal. So if I'm on one side of this transversal, my same side angles are these two. Now notice I'm using different bubbles. I used a single bubble and a second bubble. They are different digits. You can see they're different. I can look at this picture and see they're not the same number. This angle is acute. It is less than 90 degrees. You can see my wedge piece is in L shape. It's smaller than L. That one is larger than 90. So they are definitely different. One's obtuse, one's acute. They are different digits. In fact, I'm going to write that down. One is obtuse, so it's larger than 90. So larger than 90 degrees. And one is acute, less than 90 degrees. You can see that. So they're not equal. They are supplementary. What does this word mean again? What does supplementary mean? I just used that word earlier when I was talking about vertical.
Adds up to 180.
Yeah. Angle 1, I'll call it, and angle number 2 add up to be 180 degrees. That's what supplementary means. You're adding 2 angles together to make 180. They make a straight line. So I'm going to put my 2 numbers in here. So I'm going to call this angle number 1. So angle number 1 and angle number 2. They're adding to make 180. That's what this thing is saying. This is what I need to prove. Right? I need to prove this is the case. That works on this picture for some reason. Using evidence. Okay. Now, there's a couple different ways to prove this. There's a couple different ways. I could use the postulate. I can use the theorem that I just talked about a little bit ago to use as evidence to help me out with this. It doesn't really matter. I'll give you guys kind of the pick. Do you guys want to use the postulate or the theorem? Those two over there. Which one do you want to use? Postulate or theorem? Pick one.
Theorem.
Theorem. Okay, we'll use theorem. Okay, I'm going to use this theorem, alternate interior, to prove this thing. Okay, to prove this same side interior. Okay, so how this works? Angle number 2. I'm going to go alternate interior. Alternate interior. I'm going to hopscotch 2 up to here. Does everyone see that? That's an alternate interior. Those are the same. That's what that theorem said, from yesterday. Alternate interior angles are automatically equal in terms of numbers. So you guys picked earlier, I think 52 and 52, right? We bounced the angle, right? Now, do you see that these two angles, this angle and this angle, are side by side? They are now adjacent to each other now, right? They're adjacent. Well, this is a straight line. We've said this earlier. That was a part of the stipulation. These are lines that are, drawn. They're straight. They're not curved, right? They are lines. What do lines have to add up to be? 180. I just proved it. Lines have to add up to be 180. Just by transferring angle 2 up using alternate interior, it forced the two angles to be side by side, to be adjacent to each other, and they made a straight line. They made a linear pair. They're supplementary to each other, because lines always add up to be 180. That's a definition of a straight angle, right? Straight lines. And again, how you know they're straight? It literally says them here. They're parallel lines. It didn't say, it didn't say curves or anything like that. So that's the concept. It's a very simple process. But what this means now is, now that you know certain angles up here, I can start transferring angles around this picture like crazy. Okay? Like for instance, I'll use the number you guys said earlier. So if this was 52 degrees, this angle is automatically 52, right? The funnel system makes this 52, and the funnel system makes this 52, right? What does angle number 1 have to be then?
128.
Yeah, right? It has to add up to be with the 52 to make 180. So this angle right here, this angle number 1, would have to be 128 degrees. This green is dying. This would have to be 128 degrees so that it adds with 52 to make 180, right? You have to do the little calculation in your calculator in your head. So then I can start hopscotching that number around. This 128 transfers. It goes alternate interior. It hopscotches through vertical or corresponding. Do you see how I can start filling in all my numbers? I know every angle in this picture if I know one of them. Just one, that's all I need. And I can start transferring everything around. That is what your Google question of the day is going to be today. I'm going to provide you a picture. I'm going to tell you one of the angles on the picture, and you have to go find all the rest of them and tell me specifically what they are. So maybe I tell you angle number 2 here is 30 degrees. So then I can start going, okay, this angle number, maybe they're numbered. Angle 1, 2, 3, 4, 5, 6, 7, right? I have them all numbered. So I told you this angle's 30, so then that's 30, and this angle's 30, and that angle there is 30. And you can start specifically telling me, okay, angle number 2 is 30, angle number 3 is 30, angle number 7 is 30. And you have to type it in your Google question. Make sense what you're doing today? Be very specific. Okay, we have one more property and then we're done. And then I'll give you 10 minutes to type in your little Google Doc. So you can type in what your numbers are. But pretty much right now, as of right now, you can answer every question. You know the concept of how to bounce numbers around. Okay. All right, last theorem today. Thank you. Okay, last theorem today. This is Theorem 3.3. Theorem 3.3. If two parallel lines are cut by a transversal, their alternate exterior. Angles are congruent. Alternate exterior now. So they have to be on opposite sides of the transversal. That's what alternate says. They have to be exterior. They're not physically next to each other. They're not adjacent. All the definitions of all our words can be non-adjacent. Not physically next to each other. And they would have to be the same. Well, if I looked at my picture up there, I have alternate exteriors. You can see them. In fact, just my example I did. This is an exterior angle. The alternate would be on the other side of the transversal. That's an alternate. It cannot be adjacent, and it has to be on the opposite side. So it would have to be this angle up here. Do you see how they're automatically the same digit? It's forcing them to be. Now the proof is actually what you're looking at up there. Because of alternate interiors, I could funnel, go alternate interior, and funnel again. So that's the reason why it works. That's the actual proof. You're actually seeing the picture up there. It uses vertical, it uses alternate interior, and then it uses vertical again. And it shows that the alternate exteriors have to be matching. In fact, you can see it. The other alternate exterior is also matching. You can see how they work. Questions? Okay, that's it for today. Google question went live. I think it went live about 5-6 minutes ago. I think that was the chime I think I heard earlier. You're going to answer the question. Be super specific. I tell you a certain angle, a measure. You have to go find all the other measures. So on the picture. So a lot of them are going to match, and then you have to find the other one using some common sense. Remember, the consecutive interior or the same side interior have to be 180. So whatever these are. So be careful. So. There you go. That's it for today. So you can go answer. So Alexis, thank you for tuning in. You can go answer your Google question of the day. Hopefully that made sense. So if you can see that. Again, all these theorems are on page 180 and 181 of your text.